Session two is about quantum estimators. And basically, we're going to look at um, different linear models. You don't have to be, well, they don't have to be linear. It's a question, can you produce nonlinear model in quantum computing? Yes, if you stick measurements halfway through, and definitely in hybrid models, you could create nonlinear models. But apart from that, models are linear, even though it could be very complex. It could be approximating nonlinear structures. But we're going to create a very simple linear model, which will produce an outcome which is a floating point number. It's an estimation of some value. And we're going to look at different aspects of that modeling. Okay, hang on. Have I talked about this? No. Okay, one issue, I want to start always with something different. When you create, I haven't talked about it. Well, okay, I hope so. Um, so when we create a model, we don't program it for ourselves. We usually have a client, and even if you do it for yourself or scientific application, when you come back in 6 months, you're like another person coming from Mars. So what we need to do is always start with a definition of the problem, the business problem that you're solving. Don't start with model development with a solution when we don't know what we're solving. So always state what you want to get and how you're going to measure the outcome, how you're going to measure how good it is. Um, Definitely get the data and study the data, understand, explore, prepare, and repair the data. So it's a classical process of analytic process. You need to discover relationships in data. Like we were talking about simple sine function, but there's a lot of relationships in between data points in a sine function that you have to understand, and you have to understand how the mapping occurs onto your encoding scheme, like angle encoding. Then we develop and apply analytic models and quantum models. It could be that your quantum model is only part of the overall overarching um, analytic solution. So definitely in hybrid systems, your quantum model is part of a larger classical structure. And we need to evaluate, improve the models, and evaluation, you need to be smart. We can't simply go around and by trial and error try different things. So it's better to have a systematic way, and systematic way could be automable. So you could automate your tests. Then you start it up, submit in the batch, come back the next morning or in a week time, and you have the answers. It integrates your solution with the rest of the process. It could be a business process. So imagine that if you have the weather forecasting model, you need to interface with very elaborate and sophisticated software and devices and reporting up to the TV and nightly news. Assess the results and possibly go back and re-specify the systems, collect new requirements. So that's a typical cycle of events in which quantum models live. They're somewhere there. Okay, we're talking about estimation, and we're going to talk about classical systems and quantum systems. Okay, so in classical estimation, it's we have a lot of models which can perform estimation of continuous numerical outputs or targets. That's in contrast to classification models which give you discrete labels. We have linear regression models, nonlinear regression models, support vector regression, polynomial regression, Bayesian models, neural networks, of course, time series forecasting, ensemble models of those other estimation models. Now, when it comes to quantum estimation models, they basically attempt to apply quantum mechanics to improve the precision, efficiency, computational power of some estimation tasks. It doesn't mean they're very successful at that. But we try to do it well for certain types of problems. And the best problems are in chemistry and physics because um, the models, they map reality very well. So the simulation outcomes are fantastic and they're very precise and highly efficient. So great, great scope and opportunities for people working in physics and chemistry with quantum computing. However, the models are especially useful in situations where we deal with high-dimensional data or noise or very highly complex calculations. And that's evident with some of the quantum advantage modeling that companies announce every so often. But applications could be many. I mentioned the best applications are in physics and chemistry and maybe in drug discovery. There are good applications in finance. So we have a few successful companies developing quantum models in finance, in banking. I'm not sure stock price prediction is very good application. I haven't seen any successful area. Maybe autonomous vehicles and definitely in energy management. So there are a lot of effort in those spaces. And there's a lot of models in QML that could be useful, in particular quantum neural networks and quantum kernel methods and many others, but we're going to focus on quantum neural networks because they're simple. And here we come to how we go about testing those models. So when we develop a quantum model, first we need to test, does the model have the capacity to learn? Okay. It could be, as we saw during the break, when people try to fit the model into new data, with this encoding, the model had no capacity to learn at all. It would abandon learning and would plateau very, very early. We discovered later it had nothing to do with the structure of the model, with the weights. It had something to do with encoding strategy. But that's what we want to do. We train the model with some data and we apply to the same data and see if it has them in memory. Can it recall the data it learned in the process? So that's the first thing, but that's not a good approach. So a better approach is holdout testing, where we split the data into three components, one for training, one for validation, one for testing. And what we do in a process of model development, we develop it with the training data. We apply to validation data to get the sense of its generalizability. And we then go back to training and we improve the model, we validate again until we decide the model is good enough. And then we apply to the testing data, which we never used before. So that's why it's called honest testing, because we apply it to the model, to the data, which wasn't used at all during training. So it's not only wasn't used directly into altering the weights, but wasn't even used for validation. So holdout testing is great, but it simply validates and tests the model once only, assuming that all data partitions represent the patterns occurring in a population, which could not be possibly true. A better way is to do cross-validation. So those people working in data science, machine learning, you know it very well. We split your available data into folds, let's say 10. We use 9 out of 10 folds for training and 1 of those for validation. And then we rotate it and we get slightly different training sets and different validation set. And we could set aside data for testing as well. The problem is that if you develop a quantum model on a simulator or even accelerator, the training could be very slow. We used very tiny model, very simple data. So it was like 17, 18 seconds to train the model. But many models take days or weeks to train. So cross-validation, it makes sense if you have actually, if you sit on a data center and you could use multiple machines, multiple GPUs, and each test would be run on a separate machine, on a separate GPU. Okay, all quantum models are sensitive to initialization, and if the model is developed, it's always good to retest it with differently initialized weights. in that process, we may actually resample data partitions as well. So if you change the initialization, it's an opportunity to change your holdout test or apply cross-validation. So each change one. At the same time, when you change your data training and you optimize your model, you don't know whether the model improved because you've done something right, or the model improved because you're more lucky with the data partition. So it's always pro and cons with this. So I would say that with the initialization testing, you develop your model well on a fixed partition under random seed, and then you go and start testing it in different circumstances. So here we have an example of a linear penny lane quantum model. The first thing is those linear models in PennyLane or Qiskit, they are not regression models. So they cannot be simply solved with a clever statistical assessment of its distribution of outcomes. So the models need to be trained and the outcomes need to be evaluated. But here we have the next step of sophistication. We know that in PennyLane, everything is a function. And we also know that certain functions like the circuit, they must actually get specific input. So we need to pass the weights and the inputs and nothing else. If you try to pass any other arguments, you're going to get an error because it is expected that the quantum model has weights and input and nothing else. Could have multiple weights like inputs, but that's a normal structure, weights and input. So how does the function know how many qubits you want to use, or whether you want to use basic entangling or strongly entangling layers? And that could be done with the use of so-called factory functions, which you can see here. We have a nested function. So here's a factory function, which within its own structure, it defines another function. And this other function is called the closure. So that the parameter values, when this function is called, the parameter values have specific values. This function is then created and passed as a result of calling this top function. The result is this specific function, which takes only weights and input, but has access to the specific values of the factory function, which created it. So it's a trick in Python, but it's not commonly known for some reason, but it's people prefer to use object-oriented programming classes instead of simple functional way. One great thing about using this as opposed to class definition is that from the point of view of differentiating the factory function or the function which was generated, this is basically applying two functions one after another. So you could actually get differential of such a function very easily. So that's actually useful from the point of view of differentiable programming and PennyLane in particular. So that's what we do here. I created a model which is created by the factory. The model is a closure. We can do the same thing with other things like cost functions and many others. So whenever you need to have extra information which is not available, or you're restricted to the parameters that you need to have, then you could use, like in here, non-local variables accessible at the point of the creation. How you create a quantum linear model from this? You basically need to create a model, calling that top function. So remember, the function is returned from it, and that function is then passed to the Q node. So instead of using a decorator, I could use a two-step creation that creates a particular model which understands how many wires, what's the entangling layers, and whether we're scaling results or not. And this creates a circuit, a node, which could be then used for other things like optimization. We also could create a shape. So here we have a created shape function, which knows the number of layers and wires and other information. It gives you precisely the shape of your ansatz. If you create the custom ansatz, write your own shape function as well that will produce a correct shape for that function. A bit of warning is that we're going to, or maybe the warning is a bit early because we're going to move to PyTorch tomorrow, and we have some issues with PyTorch here. But here is very simple. Oh, maybe the warning is applicable here. In PennyLane, the shape of the function, the shape of the model, it takes only 3 arguments. It's only three-dimensional. Number of layers, number of qubits, number of parameters. If you want to have a 4-dimensional shape, to have a, let's say you're going to put angle embedding interweaved with re-uploading. That will not work because angle embedding already is a 3-dimensional, especially the strongly embedded, is a 3-dimensional shape. So you can't add it and you can't multiply it because that sort of implies that it's a layer with layers inside. So for that, you need to have a different way of dealing with that. Okay, so how we do, we created here the model and the shape. The model comes from the factory. We initialize the parameters with the correct shape as given by that function. And we could draw the circuit or we could start optimizing it. Okay, so slightly different way. Of course, we need to know what is the simulator we use, what is the device we use, and there's an option to specify number of shots. At the moment, number of shots is none in my settings, but it could be 10,000. And you'll see that your simulation, your basic execution and will be much, much slower. How do we train a quantum linear model? It's quite simple. We start with random seed because we want to predetermine outcomes so we could repeat it many times. We select an optimizer, and there's a lot of optimizers in PennyLane. And if we interface it with PyTorch, we have many more optimizers available. Virtually all optimizers in PennyLane are gradient-based. It makes sense for differential programming. We define the cost function, and here is the cost function. In fact, I use the cost function generator. So here we have, again, function within the function. So that's actually what's useful here because I could pass the cost function must take exactly the only parameters, inputs, and targets. If you also want to pass the model into it so that we know what model is applicable, then we need to specify it independently. Okay, so I have a 2-stage production of the cost function. It's a factory. So cost function is function with specific model and specific cost, which could be passed in. So we could pass different types of cost at the time of creation of the model. And the training loop as a parameters initialization. Training loop as before, but this time I'm going to not only keep the history of cost, but also keep the history of the parameters which were being improved at each stage. And then within, it's again optimization, optimizer, step and cost, the cost function, the parameters, append the cost returned, append the parameters, and print some data. Why should we keep the parameters as we develop? So when the model gets optimized, we'll have only a series of costs as a mean square error saved up. And only for the training data set. What if we wanted to use for test data? Where do we get it from? So what we can do is to then repeat the creation of the model for every single parameter which was produced in this cycle and create the model, apply it to the test data, generate predictions for test data, accumulate it, and then create the new performance indicator, which could be mean square error for test data, it could be R-squared or any other statistic you could produce. So that's basically what we use. Just a comment here. Here in this structure, if you're familiar with a typical optimization of the model, we would have a few steps. There's a forward step of the optimizer in which we apply the model to training data. That actually happens here in this step. We actually apply the model and we get the cost and the next parameter set. We also have the cost calculation also happening here and the step backwards to improve the model parameters. So it's all wrapped up in step and cost function. But tomorrow we're going to decompose it into 3 steps because in PyTorch that's more convenient. We could also specify the interface at QNode creation. We could say gradient package should be obtained from PyTorch. Okay, so that could be done at the point of the creation of the QNode. And we could also specify differentiation methods like use parameter shift or use something else. Also, device could be defined in the previous slide in which we could specify what type of simulator you want to use. So it's not difficult. We'll show you that in a demo. Now the performance, okay, so we need to score the model. The scoring is basically getting the model structure, set the parameters values to parameters from the saved list, or apply it to data of your interest, whether it's a training data set, test data set, or validation data set. Get the predictors, compare the predictors to expected values, and get the statistic. So here we have we did the scoring as a separate exercise. And so we calculated mean square error on training data. That came directly during training because we used mean square error during training to guide the optimizer. But also we could later apply it to test data for every single model that was considered during training. And we can see that both test data and training data, they converge nicely. We did the same thing with the calculation of R-squared. Very appropriate to calculate for linear models. Okay, so the key here, never trust your luck. You've got a beautiful converging model. And we're setting here and start publishing papers. Okay, here's an example with my colleague and past student. We were looking at 4 different ways of battling barren plateaus. Each approach was to develop the circuit in different way. Each method generated quantum models. Now, we had some good results. And then we thought, okay, let's apply to different data set. But also for each model, let's apply it to, let's create model instances, each instance being initialized differently. So we had a few dozens of models tested. And then when we plotted it, we can see that there's a lot of variance between the performance indicators. So like method 1, it's a huge variance. And it gets better. So eventually the variance reduces during training. But some methods, they come very consistent. They produce a single line every time. That's because that method had 0 initialization as part of the method. So that's actually, it's a good plot. It indicates not only the model converged, but also what was the variance of results while it's happening. So depending on the initialization, we have the method more focused or more widely distributed. So that's one thing, never trust your luck. The other one is don't get too cocky if your quantum model beats the classical model. There's a lot of papers which say, hey, I developed this model X, and then I developed the classical model, it beats the classical model in no time. Now, some of the papers nowadays, they request a submission of your code. So I looked at some of the code. People adopt the vanilla classical model and use it as it is. And as they find, yep, I spent 1 year tuning that quantum model, compare it to vanilla classical model, and the classical model is worse. My principle is you should spend as much time tuning your classical model as the quantum model, and then tell me which one is better. And so far, with the data I've been using, if I get my quantum model approaching the classical model, or maybe slightly better, then I'm lucky. You really need to find the problem where the quantum approach matters. It's actually contributing in a very significant way because it either is close to the phenomena that you're trying to represent and model and simulate, or because your data is quantized to demonstrate a completely new way of representing data and the phenomena that normally in a classical way you could not bypass some barriers. So yep, please compare your quantum models versus classical models, and then we'll see which one's better. The next issue is the curse of dimensionality. The dimensionality in quantum models is to do with the number of parameters. Those parameters are non-local, as mentioned before. That means that you change one parameter and the other one, or every other one gets changed as well. So that's a very difficult training situation. But the problem is that as we increase the dimensionality of your model, that means number of parameters, the cost landscape flattens. Why does it flatten? People say it flattens because we do random parameter initialization, or it flattens because we have too many qubits, or it flattens because we have too many layers. That's not really true. It flattens because of the geometry. So what happens is that if you consider an n-dimensional ball of a specific radius, if your dimensionality is low, let's say you have a 4-dimensional ball, that ball has certain volume inside. And here's enough volume to plot the surface in lower dimension of 4 dimensions. When you start increasing the dimensionality, what you find out, you could actually calculate it, is that the volume inside is reduced. So that's actually counterintuitive. The volume available in 45-dimensional ball is very small. It's so small that when you put another a layer inside, it's completely flat. So you can see here we have a lot of space to play with. Here we have very little space inside that n-dimensional ball. You could actually calculate distribution pairwise of pairwise distances between points within n ball. And you can see that the distances shrink and they concentrate around the mean. So there is a completely flat space inside. So that's geometry. Geometry says the more dimensions you're going to have, the flatter is the cost landscape. That's basically it. And you can't actually jump over it. What you can do it is to start cleverly splitting your dimensionality, measure it differently, reduce number of qubits, layers, parameters, reduce number of entanglements, the CNOT operations. Also remember why random parameter initialization does not work. Because in the flat surface, unless you're very close to your minimum, it's very hard for the optimizer to move you from the random space to the space close to the minimum. So in a highly dimensional space, you need to start close to the minimum. So for example, if you have in quantum chemistry, you start calculate your parameters classically the best you can. So you could get very close to the minimum in a quantum model and only then start optimizing the quantum model. So you can just push the ball and just goes right into it. There's also some Barron plateau resistant models like quantum convolutional neural networks. And that's because the modeling uses the filter which moves around. The filter is small. It reduces the dimensionality of your problem. Okay. Whatever you do, whatever model you develop, it's important you develop some diagnostic charts that could tell you how good or how bad is your modeling. And so those of you who come from R, perhaps in analytics, R as a language is full of those diagnostic charts. So you could actually check whether your regression works. But in Python, if you use scikit-learn, it's got a lot of tools as well. So, but here I have some tools I developed myself. It's a very simple. You could look at the distribution of data before and after training and calculate residuals. The residual is the error rate between expected value and the actual value obtained. And then you could look at how far it is from perfect. So if you have, this is the line, this is the line of expected values, and you look at the residuals in terms of expected value, one dimension, and obtain value, the difference from the expected value in other dimension. You can see the distribution. You can see that before training, the residuals were like scale up to 100%, and after training, we have up to 20%. But that's actually is not very useful because it shows you dots in the space. It's much better to look at similar information, but in aggregated form. So if you look at the residual histogram, you can see the for training and testing. So you can see for training, it's pink. Most of the residuals are zero, close to zero. So a good result for training, but for testing, there's a lot of small errors peaking around 5. So it's not a very good model. It's not bad, but it's not perfect. We also have some outliers still far away from the zero residual. You can also look at, so you can see the severity of errors in testing as opposed to training. You can also use that chart, the truth versus prediction charts. You plot your truth value is a predicted value versus expected value. So you plot the truth versus truth, and then plot predicted value versus expected value as a line winding around the truth. So what you can do is how far is the prediction from the truth, how severe it is, and also at what value of predicted value it's worse. So it gives you a lot of information. You could go back and try to fiddle with your model and maybe your data. So there's lots of barriers to quantum estimations. One barrier is to do with VQA, the variation quantum algorithm and the training. And we have a quick step forward. That means returning the value. And that's usually done in quantum simulator on the quantum machine. We have a slow step backwards, training the weights. And of course, now simulator, everything's bad on a simulator. What's the solution for this, for the slowness of training? First of all, we could rely on true quantum gradient-friendly facilities like quantum native gradients, quantum native optimization. It's difficult to use and on simulators much slower than but theoretically, this is a much better way of solving the problem. Parameter shift rule is universal. It's actually a good gradient to start with. We could look at hardware efficient differentiation. So that will be delivered by GPU manufacturers. So if you use CUDA, it will have some gradient efficient differentiation method recommended. You could use quantum kernels as opposed to quantum neural networks. In quantum kernels, it's a one-shot training because there you train the feature map rather than the logic of the, still you need to train something. You could also use quantum annealing for training, or you could use quantum annealing for pre-training of the model to get close to the optimum and then use gate-based machine for the next stage. You could use Boltzmann machines, so-called Gibbs sampling, use time evolution-based gradients like trotterization. So rather than having loops, you increase the size of your ansatz. It's bad because it decoheres quickly. Use adaptive trotterization. So there's lots of methods and solutions to the problem of training and the slowness of the training. The next problem is precision for estimation. So number of shots is the key. The more shots you have, the better is the result when you actually run it on the real machine or the accelerator. Here we were running on a simulator which used some knowledge of statistical distribution of it knew what should be the result. So more shots, more precision, but more slow. We could use continuous variable quantum computing like in photonics. You could actually get continuous variable out of the circuit in a photonic machine. We could use analog quantum computing like neural atoms, photonic systems, quantum annealing. You could also, when you have a superconducting machine, on some of them you could tap to those resonators and you could actually get continuous values out of resonators, and use Hadamard test and iterative phase estimation. So there's things to improve the precision. Finally is the noise. One simple way of overcoming noise on a real quantum machine is to train the models with simulated noise. So you simulated noise you expect to encounter later, and you could apply some error corrections and error mitigation techniques to eliminate that noise. Now, we have other data available for you. So we have Pendeley demo. The data set is three-dimensional linear data. And there's another data set. It's a Swiss roll. It's a more difficult data set. Plus, there's a data set for real estate price estimation. So you could play a lot. It's a challenges for you. We're not going to check how successful you are with all those challenges, but they're good data sets to hone your skills on. So let's go to the Pendeley demo, and that will be done hopefully quickly. So let me restart the kernel. Someone wrote on my screen, I'm afraid. I apologize. We have yellow. I'm not going to find out how to remove it, but I'm sure you could remove it.
I will try to remove it.
Okay, thank you. Okay, so we have a simple quantum estimator. The tasks are simple. We create an estimator. I'm going to walk you through the basics, and then you could try to improve it, improve different aspects of it. We could change the encoding slightly by encoding the margin around the encoding space. And we could do the mean square error R squared and calculate them. It has a lot to do with machine learning and less to do with quantum machine learning or quantum computing. But let's look at it. So we're going to, that initial step is to, so you could access the utility file. Depending on how you're going to run it, it may be needed or not. So again, I'm going to have a lot of additional functions. I don't know why I still have NumPy and NP. At some point, I wanted to use a standard NumPy. So I simply imported NNP, but I eliminated it. So that's not needed anymore. I bring in my utilities. There's a utility file with a lot of functions for plotting and for drawing the circuits. And the Pendeley, again, we import NumPy as NP, redefining NumPy. So if you wanted to use both for whatever reason, you have to rename one of them differently. And I'm going to use sklearn for some metrics, and I'm going to use the data set from sklearn, scikit-learn. Okay, so let's get the data. And this is what the data looks like. You can see it's plotted nearly on the plane. It's in 3 dimensions. We have a number of data sets. The whole idea is to predict, given feature X and feature Y, predict the value. But of course, we have the value in the 2 dimensions. So that is the problem here. And again, I'll show you where the tasks are. So first of all, we're going to do some settings. I'm going to encode the data around the zero around the zero x plus angle, from minus pi. No, sorry, around the pi, I think. Zero margin. We add angle and we deduct angle. Yeah, for some reason around the value of pi. So that's actually, and what happens on the edges, we have some margin, and I can take the margin, increase it or reduce it. That's actually what's useful is that once you start rotating this in a 3-dimensional space, each qubit, if the margin is not small, you're going to sometimes skip over the z-axis and get some ambiguous readings. You could increase that value. We're going to have as many qubits as there is features. So there's 2 features only. We could play with the number of layers and start with straight away with more complex entangling. So this is actually real data. So we start with some pre-processing. We're going to scale the data to our angles, or required angles from here, the minimum and maximum angle. And we could reuse that fit later on if needed. If we needed to go back to original units. We're going to create the partitions of data for training and testing. And we're going to turn all data into tensors. Now, because this is the data as input, we don't require any gradients. This is just values. If we were going to create the weights, we need to use gradients because the optimizer will be manipulating gradients. And we have, as before, I showed you, we create the cost function factory. Specify what type of device I'm using. Again, default qubit. A lot of comments explaining what I do. And here's the model, which I explained before. Again, it's a function factory. It's a factory of quantum models, which we could have strongly entangled layers or basic entangling layers. And we also have utility function to tell us the shape. So we don't have to go around and changing comments as we did in the previous notebook. So here what we did is create the model, create the circuit or the Q node, specifying on which device is going to this model run, and find out the shape, knowing how many wires, how many layers, and the shape is specific because it understands what type of entangling I requested using extra parameter. And here's a test. I create the test weights. See here, I require gradients to be true. And we draw the circuit. It's a utility function from my utility file. So I don't need to produce all the other additional statements around it. He just produces nice circuit diagram. Remember, it's required that we pass parameters in as if you're calling the function. As you're calling the function, which generates the circuit, which it does. Okay. Now we could create the training loop as we specified. And it's much slower than before because the data is more complex and the circuit is more complex. Okay, so it's all to do with the data. We have actually more data. We have 300 data points here. Before we had only 64. So it's actually converging quite well. We can see the cost is reducing. And I can't remember how many epochs are requested. So if you're going to run it, see epoch number 100, you may want to set to 50 straight away. So if you have a laptop, set it to 50. So here it's not only is slow, but it prints feedback every 10th iteration. So if you have 50, it will be every 5th iteration. I'm getting good results here straight away. So what's the point of playing with it? Is 001 good enough for us? It's going to be 0004. Okay, finished. I'm waiting for the last statement. Oh, because the last statement I print here. So we have 100 epochs, and the minimum cost was pretty good in 85 seconds. It felt much longer. So now what we can do is, because we saved all the parameters, we can start producing other types of statistics. So we could get training R-squared statistic. So what we do, we simply get some parameter, the next parameter in the range of saved parameters, apply the model structure to the next parameter set, plus to all of the values in the training set. And now I'm using actually R-squared score from scikit-learn. Remember, in the previous session, I said we created by hand the scoring function because scikit-learn does not understand gradients. That was necessary for training the model, but for scoring the model, we no longer train the model, so gradients are not being used. So we could actually use the whole richness of scikit-learn to produce a lot of statistics and indicators. And then we basically append it, and we're going to show it. Here's the result of the last one on training results for R-squared. Now, your job will be to try to use the saved model and saved parameters to calculate similar statistics for testing, and then you will be able to produce those charts. At the moment you can't because we don't have any testing data. And you calculate residuals, and you will be able to produce the charts for distribution of residuals. So you have a few machine learning tasks, and I'm going to guide you through that in the next session. So we have here now, we have a bit more than half an hour, maybe. We could leave slightly longer, maybe. But you could actually continue that later at home. You have the whole Saturday, and tomorrow Sunday is for the next session. So let's start the practical session. If you understand what needs to be done, what needs to be done is listed here, all tasks. Can you improve the selected model by changing entangling methods, basic entanglement false and true, changing number of qubits wires, changing number of training epochs, changing the optimizer. Which of these changes had the greatest impact on performance? So that's actually simple because it's very much what we've done in the first session. The next one is, which could be done even first, change the data encoding by increasing the encoding margin. So make the encoding more narrow, in a more narrow scope. That will avoid some impact of rotations due to optimization. And then do calculate testing mean square error and R square errors for test data, create plot of residuals, anything you like. It will be much harder for data set 2. So that's actually a challenge task. You could also try to change the model by incorporating reuploading ansatz, which we did in session 1. See what works for you. Okay, let's get into it. It's clear what needs to be done. Hands up. One, two. Okay. We'd like to have a dozen. Okay, we have a few people. Okay, the other people I'm going to walk you through step by step. And I'm going to leave you, hopefully we can finish quickly, but half an hour looks like a challenge. So let's get into it. If you feel confident, definitely go. The challenge, the task number 2 is simple. Change entangling method. Okay, what entangling method have we got now? So we need to look at this is where the data was generated. And here we have basic entanglement false. So we already have complex entangling. If you look at the structure of it, you can see that the 3 parameters per rotation, I would say probably, yeah, let's test it, but probably we're not going to get any better. Basic entanglement truth. If we run this whole thing, I'm going to reduce number of epochs to 50. So we get answers quicker. And to restart kernel and run all examples. Oh, that was a bad idea because I'm going to get errors later on because there's, or maybe I've done it actually. It will be error on your machine, in your notebook, because I have actually implemented this. But in your case, executed only up to training. Okay, so in your case, don't run it all through because only this part is implemented and the rest you have gaps. So this is the last point of execution. You could step through this. So what we get, we have a training result, which is actually, I didn't record it. Anybody got the previous one? 006. It's very, very similar. Looks like it produced much quicker. And this is only 50 iterations. So it's 0.7 for 50 iterations. If I run it with false, okay, we have a problem here. So we can't do this because we need to actually restart the kernel each time and do it from top to the bottom. So let's run it up to this point, and then we can step it through. We have some problems because we are reusing some of the data. So we back at training. So now this is the 50 epochs training with a strong entanglement, 3 parameters per rotation. We had 007 at iteration 50. And clearly, the more parameters is probably giving you better results. Yeah, I had error because I wasn't executing from the top. So I cleared the kernel and I ran all the cells from above up to the point. Okay, so what we get here is actually the minimum cost is much better with than with a single parameter per rotation. 3 parameters per rotation is a richer model. So clearly has a huge impact here. If we try to, we can't actually change number of qubits. I don't think so. Not in this particular model. And this is because of the way the model is constructed. So basically, I'm creating angle embedding, a specific size, basic entangle embedding. So angle embedding and entangling must have, in this model, must have the same number of qubits. But because we have only 2 features, so we would like to have data embedding to be on fewer qubits than entangling and the training block. That's possible if we had a manual loop here, which creates parameters on the number of qubits that is required for the task. So you could have more qubits than your input size. That's possible, but can't do it with this structure of the model. Okay, so we can't have number of qubits different than number of features in this model. Okay, so one task goes away. It can't be done unless you change the structure of the model. But we could change the number of layers. So you could see what happens if we have more layers. Let's make it, I'll make it 8. Restart the kernel, run from above. So all cells above are executed. I'm going to step it through. Now the question is, can we do better this time? So more layers, more parameters. We increase the dimensionality of the parameter space. That probably means we need to have many more epochs to deal with, but the model is more expressive. So that means it can represent more variety of different data sets. It may not train in 50 epochs to the same extent. Okay, how do we get R squared around 0.98? I must have trained it better. I have here, I'll explain that in a second. Okay, so here we have the minimum cost 0.3. It's not bad. It's slightly lower, but not significantly. Someone had problems with very bad results, and it's possible that's because using a single parameter per rotation in the trainable block. I here have false, that means use not basic entanglement layer, use strong entanglement layer. That means 3 parameters per rotation in the circuit. And it's probably got the result from the simple model. Okay, so we have 3 parameters per rotation. In the training block, we have here 8 layers. Where's the code for calculating testing MSE in R squared? The code is what you need to write. Okay, so here I have example how to score the model. So we created and trained this model, Q-linear model, and we saved all the parameters which appeared during training into the history of parameters variable. It's a list. So from the first iteration to the last iteration. What I do here in the loop is to go through the parameter list and apply the parameters, and in this case is a training set to the model to get the predictions, and then I could compare the predicted values against the actual values to get the R-squared code for the training data. Here, I say calculate it yourself. So you need to figure out how to do it for test data. It's very simple. It's automatic. Here's just R-squared, but we want you to do mean square error as well, which means that you could use another function from the scikit-learn for mean square error. Make sense? Okay. So we've done a bit of experimenting with well, we can't change qubit wires unless we change the model, but it's not difficult. You could do it. We were changing entangling method. The more parameters per rotation, we get better outcomes. I didn't see much value in increasing layers, but maybe it's a possibility. Giving more training epochs. I'm pretty sure that if we give more, so I'm going to do it because I can. In my case, I have a fast machine. Let me just increase it to 150. Run all above. And that will require, I'm going to check what was the last result. So here we have, okay, it was epochs and training the model. The best result was below. So I got here, the minimum cost was 0.003 at 50 iterations. Now we're doing it much slower, which means you could actually start working on calculating, scoring the model for test data. Once you got that, you can also plot. So have the plotting functions ready for you. Are you working? Well, clearly after 6 iterations, I'm getting already better cost than before. So definitely having more training iterations, we get much better outcome. But you can see it's slow. So it took 103 seconds, double amount of time than the 50 epochs. So today we're trying to get familiar with PennyLane and get idea how the process of model building works. I can see that we have big chunks of code being executed. So I'm not going to develop things from scratch because we're working on near real data. I'm not going to give you iris data because we know it's going to get trained. We're trying to use data which I actually added noise to this data. So there's a level of noise injected to this three-dimensional data. If you're going to work with Swiss roll, it's a lot of problems there. First of all, how you actually encode it, because we have color and shape. You can see now that after 100 iterations or 75, we get a lot of repetition. So probably the learning plateaued and the model stopped learning. We can't get much more from it unless we do something different. Okay. So what's the result here? So we get an improvement. I think that the last one was 0.003. So we got this 10 times or maybe 5 times better outcome. So more epochs may work, but after a certain point, there's no point. So you can see the best epoch was 132. So actually it was somewhere around this space. So it was still learning even though we didn't see it. But it's not far, 0.0008 and 0.001. So there's a definitely a dip if we plotted this, which we can't because we don't have a test score. Has anybody worked out how to calculate the test scores? Have you done it? Nobody. Okay. This is the magic of test score calculation. So we prepare the list. Where you can initialize the minimum and the maximum. So minimum for mean square error because we want to minimize that value. The maximum for coefficient of determination, R squared. Look here, I'm using the infinite value, the float and P infinite for mean square error. We could have used 1000 perhaps, but we don't know what is the scale of values there. So I use here infinity. Here set iteration to -1. Thanks, Tomek. And here I have a negative infinity. And before iteration 0 starts, I set it to -1. And it's very simple. In a loop, we go over the parameters, the list of parameters, history of parameters. We get the next parameter from the list. We apply the model given that parameter set and the test set, tensor. So it has to be tensor, not just an array. That's why we're converting to tensor. And then we could apply scikit-learn scoring. So one is R-squared score, that's straight from scikit-learn. Another one mean square error. So to get the to basically compare the prediction against the truth. In both cases, we append the result to appropriate list, and that could be it. But if you wanted to also keep track of the minimum and maximum iteratively, we can do it this way, or we could simply leave it for later and do the calculation like this. So we could find the maximum value and find where the maximum value is. Okay, so I did not have to calculate it at all in the process. So that's a very simple structure. You could copy parts of it from here and simply change the names. Execute it. It's quick. And then plot it. Okay, why are we using all parameters for training? Because those are the only ones we have. Those are the parameters the optimizer generated for us. I don't have anything else. So what I want to do is to calculate the test scores using the models we generated during training. Yeah. So we generated a lot of models on the way as the optimizer was navigating the landscape of costs. So every single model on the way down, we picked up the parameters which created the model, we saved it, and then we could use the same parameters to recreate the model from that point during optimization process. Shouldn't we only use the one that is the best with the lowest loss? No, because the lowest training cost may not be the best testing cost. And in this particular case, they will be identical, probably. However, in many other cases, the model overtrains, and that means that it stops generalizing, and so the test scores are going down. So in this case, the optimal model for applying to new data will not be the best training model, but the best model that comes with the lowest test cost. So here, if you look at, okay, for example, here, what you can see is that when it comes to R squared, the best test model that the test R squared was generated at iteration 76, whereas the best training R squared was generated at 131. So definitely they are not coming from the same model. In here, we can see that it's the same situation. The minimum mean square error for training was at 132nd iteration, whereas the minimum for test data was at 76 iteration. Okay, some people want to see that code again. So you see the point. So those people who come from quantum computing background, you need to look at the purpose of training. Okay, the purpose of training was to apply the model to the training set, and we use the optimizer that navigates the landscape of errors, the landscape of costs. The cost indicates how bad is the error of prediction. So definitely the model is improving all the time. And at some point it's overtraining. What it means is that it gets better and better training on the data it has, but it gets further and further away from the data in the population which the test set is representing, the data it did not use during training. So the model starts getting biased towards the training data set, and it specializes too much for the data. It simply memorizes the data. If you give enough capacity, enough parameters in this data set, it will memorize this data perfectly. That's what often happens with classical neural networks, because they have a lot of parameters, they learn very quickly, and they're overtrained very, very quickly. So we have much fewer parameters here, but those models overtrain as well. Okay, so that's actually was a useful exercise. For the model should be generalizable to the population, to the data it had never seen during training, and the test data here or validation data could be used for that purpose. Okay, we have one more message here. Okay. Now, when it comes to residuals, what's the residual? Residual is the difference between expected value, the true value from my data set, and predicted value. So that's difference is the residual. So what we want to do is to plot expected values, the values of the truth, versus the difference between prediction and expectation. Now, in my case here, I normalize it and present as a percentage. But let's first produce residual chart where we calculate the difference between expected and predicted values. So we need to predict the values for both the training data and test data, and simply do the scatter plot. We actually have the scatter plot here, in which we have the blue represent training residuals, the red representing testing residuals. The next step, we're going to worry how to normalize it as a percentage, and whether or not we want to show the units in the original value. So when we do work with residuals here at the moment, we work with them, it's a transform units. So remember at the very beginning, we transform the units in the data preparation. So we scale them down, and then we split the data and turn them into tensors. So what it means is that when we calculate the residuals at this point, if you want to present as a percentage, they're linear scales, so it doesn't matter. You could use the scaled units and then initially show them as a scaled units y-axis. But then if you normalize it, you're going to get this chart. If you want to have the actual value of residual, you need to actually untransform it, transform it back to the original units. For that, you need to look into some manuals online. So I'm not going to ask you that right now, but you can do it at home. So to calculate this would be very simple. We want to get training differences And we could calculate two vectors, yeah? So expected values, but first we need to calculate predictions for training, then predictions for testing, and then there would be residuals for training will be, okay, so we need to get some tensors here, or the actual values. I can actually show you the code. Maybe simpler because we have 2 minutes to go. So the same thing as before. I got into history of the parameters, and I'm going to get the parameter which gave me the minimum mean square error for testing. So this was the best model for testing, most generalizable. So that was calculated before. So here I was calculating what was the value in testing and what was the iteration. So the minimum mean square error was calculated here, and the iteration at which it occurred was remembered as well. So I have these values. I know what is the best model. The best model is the one which gives me the minimum mean square error in testing, because it's most applicable to data not seen before. So this is the optimum test parameters. Now I could use those parameters to apply the model and apply it to testing and also to training. So the best model for testing and training at this point. And then I could, if I want to work with the original units, I need to scale them back to the original units. If I want to work with percentages, we can skip all of this and simply calculate residuals as a percentage value in some range. So here I gave the range from minimum to maximum, and so I used that as a reference. But you could work out in different range. But here I have inverse transforms of the scalars. The scalars were saved at the top. When I was scaling the data from the original units to the units which are suitable for data encoding, I could actually inverse those scaling back to the original units for the predictions, the true values, and so on and so on. Reshape it into appropriate shape, lots of reshaping, and then calculate the residuals. Okay. You can use the same data for other plots. It's simply using data plotting as histograms, and then using the same data to plot the difference. It looks a bit different than what I showed you, because it's different training. So that's session 2. I recommend you try to complete that, especially people who are not skilled in machine learning. It's a lot of learning about how to structure the data, how to plot the data. It's a useful task for people who did not come from machine learning background. Tomorrow we're going to do more complicated tasks. So normally classification seems to be like the easiest one, but in our case, it will be more difficult because we will be trying to integrate classification with PyTorch models. So we're going to create the Penelate models, and then we're going to inject them into PyTorch neural networks as a layer of PyTorch neural network. So that's actually useful because you can start creating models which are hybrid. The models which have classical layers, there's a layer of quantum layer which could perform a specific task. For example, the task in higher dimensional space. And then you could apply more classical layers. And we're going to apply that concept to reservoir computing. So we're going to look at how to create a reservoir model. It's a model which we can use quantum. We can use the. Okay, someone's going. We could use the quantum model to expand dimensionality of data. And we can actually do it in a very tricky way because rather than training that model, we're going to create it with fixed weights. We're going to create a model with random weights, and this model will expand dimensionality of data. And then we could apply very simple classical model because there's linear separability in high dimension, a bit like kernel methods. And so we could use very simple classical model to actually do the predictions. So that's for tomorrow. So we are coming to the end. Pavel, we are finishing.
Yes, yes, we are finishing the first day of our workshop. So Jacob, first of all, thanks for the great lectures, the great sessions. Yeah, I see that the feedback is quite good. And well, we also thank all the participants. I see that now we have much less participants that we had at the beginning. We'll see how many participants we'll have tomorrow. But tomorrow we'll start at the same time as today, so it's 10:30 UTC plus 2 Warsaw time. We hope that you will join us as well. In the meantime, if you have any questions, please post your questions on the Discord. We'll close this Zoom soon, but our mentors should be available on Discord. Maybe not. Maybe there could be some delays in the answers because they will not be available all the time. But we should be able to provide the answers in the asynchronous mode, hopefully. Uh, I think this is all for today.
Yeah.
Or Jacob, is there anything else you would like to
No,
add?
it's all good. So uh, don't work too hard on all the problems I gave you. And tomorrow is another day. And in a sense, it's independent. Well, what the lessons learned from today is how to construct those models and how to layer them, because we're going to use almost the same structure, except that the new phenomenon will be PyTorch model structure. Okay. So we're sort of building up scaffolding the learning, unfortunately, in a very rapid pace, I imagine. I imagine that the two sessions could be spread over a week each, but over 100 people sustain this pace, so you're doing well.
Yep.
Thank you. See you
Great.
tomorrow.
Thank you. See you tomorrow.
Thank you.
Thank you.